Hello everyone. This is lesson 4 of solar energy application course. Within the solar radiation section, this is part 3, and we are still continuing the discussion on sonar geometry. This is our textbook, as mentioned before, with some additional references. In the previous session, we discussed about the location on Earth and coordinates, latitude and longitudes, and their effect on our solar calculations. We discussed about solar time versus standard time. This is a very important topic. Introduced major parallels of latitudes like Tropic of Cancer, Tropic of Capricorn, and others. Declination angle was introduced. We discussed about seasons, and I showed you a very interesting movie. You may see it if not yet watched. And some important angles in solar calculation were introduced. Today we want to learn about some important angle in solar calculation in continuation to the previous topic. Sun path diagram is introduced, and you can see that how it's important in our calculations. A short discussion on solar tracker or solar tracking, and shading in solar modules and solar collectors will be introduced. If you remember from a previous lesson, we introduced two angles, as you can see here in the graph, in the picture. These are slope. Slope is the angle between the panel or collector with the horizontal, and is shown by beta in this course. The other was gamma, which shows in some way the angle or direction of the solar panel or solar collector, and the reference, as we may remember, is true south, east negative, west positive. Two more angles are introduced today, or three actually. These are the angles which specify the sun position in the sky. The first is theta z. Theta z is the zenith angle, and actually it's the angle between the vertical line and the line to the sun. The vertical is called zenith or khat ras, which I think in Arabic is also the same. So the angle is named Zawiye khat ras or zenith angle. The complement to this angle, which is alpha s, complement means that adding it to theta z, the result will be 90 degrees, is alpha s. Alpha is the solar altitude or solar elevation angle, which shows actually how much the sun is above the horizon. So it is the angle between the horizontal and the line to the sun. Generally we use alpha s instead of theta z, while both can be used also. The other angle which shows the position of the sun is gamma s, and it is solar azimuth angle, which is the angular displacement from thought of the projection of the beam radiation on a horizontal plane. So if you make a projection on a horizontal plane, then the angle with the true thought will be shown by gamma s. Similar to gamma, we take east negative, west positive. So in the morning before the solar noon, gamma s value will be negative, and in the afternoon the gamma s sign will be positive. So these are the two important angles, alpha s and gamma s, which shows the position of the sun, beta and gamma, which in some way show the solar surface collector or module situation. Two methods we introduced to determine the sun position, I mean alpha s and gamma s. The first is using formulas, we will show it in the next slide, and the other is sun path diagram, as you will see later today. If you want to use formulas to calculate the sun position, these formulas may be used. Sine of alpha s or cosine of theta z, as they are complement, is calculated by the first, and gamma s is calculated by the second one. You know all the parameters in this equation. For example, you may remember that delta is the declination angle, phi is latitude, omega is the hour angle, and sine omega here is either +1 or -1. You should check if omega is more than 0 or less than 0. So in order to calculate gamma s, you should first calculate omega. Actually, you need it because in the first formula you also need it. And then check if it's less or more than 0. Then according to that, you may select the sign of omega according to what I written here. And then omega s will be also calculated. So it's very simple. At any location, which determines phi, at any time of year, which then you can calculate delta, and at any time of the day, which specifies omega, then you may calculate gamma s and alpha s for that situation. As I explained before, there's a second method also for sun position calculation or determination. It is by sun path diagram. Sun path diagram is actually the path of the sun, the apparent path of the sun in the sky. This interesting and nice picture is a solar graph exposed over the course of a year, shows the sun path of diurnal motion as viewed from Budapest in Hungary, and you can see that these are the sun paths during the year. The lowest one, as you may remember from last week's lesson, is for 21st of December or 22nd, and the highest one here is for 21st or 22nd of June. So if you in some way draw the paths of the sun, the apparent path of the sun in the sky, the result will be named sun path diagram. There are actually two types of sun path diagram. The first here in the left is the Cartesian or orthogonal, and the next here in the right is the polar. Both are possible. Actually, it depends on the position of the observer, which observes the sun path in the sky. But in this course, we generally use, or at least I prefer to use this one. The other one has also many applications in architectural calculation and other, but as we are just using it for simple calculation, we prefer to use the left one here. How to draw sun path diagram for a location, because for any location it will be different, completely different. There's a very good and well-known website. You can see the link here. I request you to do this also yourself. Actually, you can go to the website as you can see here, and then it's very simple. You just enter some data here, for example, for any location, desired location, for example, location with the latitude of 35 and the longitude of, for example, 52, or you may look up for the location. Then you may select the time zone. For example, it may be 3+30 for Tehran, for Iran, and different types of drawing you may select. You may select to draw the curve based on solar time or standard time. Both are possible. The extent of axis, vertical and horizontal axis, and many other things, the colors, and finally you may write something here if you want, and where to put the label, and two types of output you can see here, which are PDF and PNG. Entering the security code here and then create chart. It will create your desired chart. It's very interesting. I request you to do that yourself also. I did it, for example, for Tehran in Iran. Sorry, you may draw it for your location also. I request you to do it for your location also. An interesting point here, which I want to show you as an example, which is very interesting and shows the importance of the sun paths, or importance of the latitude or location on the type of or the path of the sun on the sky, is the latitude of the location. For example, I consider two cities here, one in Tabriz in the north of Iran and the other in Chabahar, south of Iran, which have different latitudes. The difference in longitude is not important in this result or conclusion which I am going to drive. But just I want to show you the effect of latitude. And if you draw the two curves for different latitudes, you can see that how they are different. For example, for Chabahar, which has a lower latitude, which is near to the equator actually in some way, you can see that sun path, especially in the first half of the year and especially for the summer, you can see that it's completely different, both in the value of the solar elevation angle and also in the shape of the curve you can see here. So you can do it for different latitudes for yourself. Angle of incidence is the other parameter of importance. As you can see here in the picture, angle of incidence, which we show by theta, is the angle between the beam radiation on a surface, which is this line, and the normal to the surface, which is this dashed line. So the angle between the normal to the surface and the beam radiation direction is named theta. And it is very important angle. Based on below equation, you can see that cos theta can be calculated by this long equation or the other one, which are the same actually. And there are some parameters in the equation which theta depends on them, which are the location. For example, you can see phi here or gamma. Phi here, which shows the latitude of the location. The day number is important, which by you can calculate delta. Time of the day is important. You can see the effect in omega. Slope of the surface, you can see it in beta. And azimuth of the surface, which you can see here in gamma, are important. So these are the parameters which finally give you the theta angle or the incidence angle or angle of incidence. It is a very important angle, and just I want to pass it to another slide here. Can you tell me what is the optimum incidence angle? Just think about that. Yes, you may be right. Actually, the best incidence angle or optimum incidence angle is the angle which makes the beam radiation normal to the surface, so theta should be 0 for the best case. Okay, coming back here. So theta can be calculated by this equation. The equation may be simplified for some cases. For example, this is the equation for cosine of theta, and you can see here, for example, if the panels for solar panels or collector slope toward the south, it means that the solar azimuth angle gamma, which is here, is 0. The last term of the above equation drops out. Why? Can you say? Yes, because then sine of gamma will be 0 and this term will drops. The other simplified case is for a vertical surface. If in this equation you have a vertical surface, then as you may remember, we take beta as 90, and the equation then becomes this, because if, for example, beta is 0, then you can see that you can simplify, for example, every term here which has a trigonometric relation with beta, like sine of beta, which is 1, or cosine of beta, which is 0, or the same. You can see that there are a lot of beta in this equation, so it will be simplified. Just as an example, you can see here an example of the case where beta is 90. You may be surprised if beta is taken 90. Yes, in some cases for facade integrated solar photovoltaic modules or collectors, you can see that beta is 90 when the panel or collector is installed on the wall, for example. You can see the wall angle is 90, so beta will be also 0. These are building integrated system. You can search for BIPV, for example, or BIPVT or BIT, building integrated photovoltaic or thermal systems. There are a lot of research on that which you can find. The other special case is when the surface is horizontal. For horizontal surface, then beta will be 0, and again you can have some simplification. For example, this will be 0, or this will be 1, and the others. And for this special situation, you can see that, as you may remember, when the surface is horizontal, then the theta will be equal to theta z. You may remember that theta z was the zenith angle or زاویه خط الرأس. In this case, special case, you can substitute theta z instead of theta. It has some application, as you can see later. And regarding from the practical point of view, I may say that generally we avoid placing solar collectors or module in completely horizontal situation. In some cases, it may be done like the one you can see here, but the cleaning of the panel, self-cleaning of the panel is generally a problem when you put them completely horizontal situation. But in some cases, especially for the location which are near to the equator or on the equator, because on the equator or the places near the equator, when phi is 0, then you may see that the sun is always overhead, and horizontal angle may be the best angle, but you should take care of a cleaning problem in these in this type of installation. Coming back to the equation for cosine of theta, you may derive also useful relations if you make some changes on the equation. You can write the equation in this form. And for the special case of solar noon, you may remember that solar noon is a time when omega is 0, actually when the sun is in the middle of the sky. For this special case, for a south-facing slope surface in the northern hemisphere, then you may calculate the theta noon, which is the angle of incidence on a surface exactly at the solar noon when the sun is in the middle of the sky. So if, for example, you want to calculate the theta or incidence angle just today, for example, in Baghdad, for a surface which is put at the slope of beta with respect to the horizontal, you can simply calculate this. Put here beta for this day, for example, 25th of June, 26th of June, you may calculate delta, and the value of phi depends on the location, for example, Baghdad, Berlin, Tehran, or any other place. And then you can calculate the theta or incidence angle at noon on a surface at this location on this day, which is installed at an angle beta. This is a very good and very applied equation. For the case when beta is 0, the angle of incidence, as I told you before in the previous slide, I think, is equal to zenith angle. It means that theta is equal to theta z, which is for the northern hemisphere can be written as this, because in this case beta is 0, and you can see that this equation is also very applied. For horizontal surface, as I told you before, you can see this, and by this equation actually you can calculate also the sunset or sunrise hour angle, because at the sunset and sunrise you may remember that theta z will be 90. Actually, it may be interesting for you that exactly at the sunrise or sunset, the sun elevation angle is 0, or alpha s is 0. As theta z is complement to alpha s, then when alpha s is 0, theta z will be 90, and then you can put here 990 instead of theta z. Cosine of theta z will be 0, and by this equation then you can calculate omega at the time of sunrise or sunset. If you show omega at the time of sunrise and sunset with omega s, which here s defines the sunset or sunrise time, then omega s can be determined by this simple formula. So for any location, for any day of the year, you can simply calculate the time of sunrise and sunset by this equation, and also you can calculate the length of the day, n. This is also very important. N is actually time between sunrise and sunset. Okay, this question you answered before. What is the best incidence angle? Actually, we saw that it is 0. An interesting point here, we will return to this topic later when we discuss about solar thermal collectors, but it may be interesting to have just a short view on that. You may remember that there are generally two types of non-concentrating solar collectors. These are flat plate collectors at the top and vacuum tube collector at the bottom. Flat plate collectors, as you can see, is a flat surface, while vacuum tube collector is generally manufactured from some tubes, for example, maybe 15, 20, 30 or something like this. When the sun hits on the collector surface, flat plate solar collector, as you can see here, when the sun takes an angle with the plate different than normal, then you can see that the case will be something like this, and the angle will be less than 90, and so the radiation received by the flat solar panel is less. But there is another case which happens with when you have a vacuum tube solar collector. Actually, because the collector tubes are circular, so in any case, either if the sun is here or here, the sun is always normal to the circle. So you may expect that the angle of the sun has no effect on the vacuum tube solar collectors, unlike the one you can see here in the left for flat plate collectors. And actually this is true. It may be interesting that this is a graph of a parameter which we name incidence angle modifier. Actually, it's a modification on the incidence angle parameter. And as you can see in the green curve, which is for a flat plate solar panel, solar collector, you can see that when transversal angle means the angle which you can see here, is increased, then the value of the incidence angle modifier will be also decreased. You can see it here. But for the vacuum tube collectors, it does not decrease, but it first increases. You can see here. You can think about that, why it increases. Because we expect that when the sun angle increases, then the value of solar radiation received will be decreased. Okay, you can see here that it is always normal to the circle or tube, so we may not expect a decrease. But why you can see an increase, even an increase you can see here when the angle of incidence is increased. You may think about that, and when we will come back to this in the solar thermal collector section, I may ask you if you find the answer or not. Actually, the question is this: while you can see a decrease here for the flat plate solar collector when the angle of incidence is increased, why you can see here an increase in the vacuum tube collector and then a decrease? I want to ask you about the difference between the two. You may think about that. You have, I think, about 1 month time, and then we will come back to this later. Okay, this is a homework for you. This is in continuation to the previous homework in Baghdad, and you can see the questions here, and I will inform you in the Telegram channel how to send the answer to me. Okay, coming back to the normal beam radiation, the case shown in the figure where the sun rays are normal to the surface or zero incidence angle gives maximum radiation exposure, but the sun apparent position is not fixed in the sky. So you cannot keep this very ideal situation all the day or all the days actually, or all the hours in a day. There's a question for you. So what is the solution to keep the surface normal to the sun rays? What's your solution? Think about that. You may pause the video, think about that, and then you may continue. Yes, this is the answer. The answer is solar or sun tracking. Because the sun moves in the sky, actually the apparent movement, And in order to keep the panel normal to the surface, then you should track the sun or move the surface with respect to the sun. There are different classifications in solar tracking system. This is a very broad topic. You can see a very interesting graph. It's taken from this source. You may refer to this paper for more discussion about the type of solar tracking system. But in very simple terms, you can see that it may be classified based on the control strategies, if they are closed loop or open loop or hybrid. Based on the drive system, which have different drive system. Actually, in general, we may have passive solar trackers which need no power, no external power, and you may have active solar tracker which needs power from output. Which needs the power from output. Actually, the topic of passive solar tracker is also a very important topic. You may search, for example, in Google patents for different passive solar trackers, and you can see that a lot of inventions are for the passive ones. But commercially, tell it frankly, most of the, or all of the solar trackers are of the active type. They may be classified based on the tracking strategies, which have different strategies. Actually, the most common ones are date and time system. Actually, by the equation that you learned up to now, you can see that you saw that if you have date and time and location, then you can simply calculate the sun position, and it is possible then to direct the surface toward the sun location. The other method is the sensor-based. Actually, in sensor-based method, a sensor detects the position of the sun, and then the tracker will be directed toward the sun. And finally, the last classification, which is my concern here, is based on degree of freedom. Actually, there are two types of degree of freedom for solar trackers. You can see that they are single axis and dual axis solar tracker. In the single axis solar tracker, you can see that there is one axis of rotation. Axis of rotation may be horizontal, axis of rotation may be vertical, axis of rotation may be any desired angle, which polar situation is generally used. The other case is two axis rotation. In this case, you can see that there are two axes of rotation. This is one, and this is the second axis of rotation. This is a picture of a real solar tracker, which I personally manufactured some years back. This is a workshop, and you can see here that this is the base of the tracker. These are two DC motors, the gearbox, and you can see that this is the tilt adjustment motor. This one is the azimuth adjustment motor. If you install the frame, it will be something like this, and if you put the panels on that, you will see such a structure for solar tracker. An interesting point regarding the solar tracker is the effect of climate on the solar tracker. Just I want to connect my power. It may take a few seconds, sorry. Okay, I now coming back, just check, yes, it is connected. Okay, here you can see the effect of tracking at different climates. The picture on the left, on the right, is the difference between a tracked system and a fixed system in an overcast summer day. It means a cloudy day, and you can see that there is the difference between the two is very small. So you can conclude that solar tracking actually has no benefit in an overcast day or climates with a lot of diffuse radiation actually. And here you can see the difference between a tracked system and fixed system in a completely sunny day. And you can see that there's a considerable difference between the two. Comparing the graphs, you can conclude that tracking effect is evident in sunny weather with enough direct solar radiation here. And the second is the effect of tracking is greater in the morning and evening than at the noon. You can see that the difference actually is here mainly instead of at the noon, and this is also an important conclusion. So we leave the solar tracking topic here, and I ask you to these or similar papers to know more about tracking systems, which is a very interesting topic. The other topic is about shading, or I think in Arabic you say tazlil. There are different types of shading. You can see here different types of shading. For example, shading from trees or buildings or something like this on a solar panels. These are at the south direction. Shading from one row of panel on another row. You can see here, for example, the shading. And some strange shading. For example, this is a solar panel which is installed nowhere. Actually, you can see that it is covered by trees, and I cannot understand how it can see the sun or how the sun can see it. Maybe when they installed the solar panel, the trees were not there, or the trees were still young, and now the trees are grown and cover the solar panel. So we do not discuss about bad installations like this one, because it's by sure these should be avoided. We are going to discuss about the shading in these specific shapes. For example, shading of one row on the other row, and shading of building or trees which are near, for example, to the solar panel on the solar panel. The first is shading in a multi-row array. You can see here a picture of a solar power plant, and by this arrow I want to show you what I mean by interspace distance between the solar panels. Actually, there should be a distance between two rows of solar panels in order to decrease or minimize actually the effect of shading, because you know it is not possible to completely remove the shading, because for example in the sun at the sunrise or sunset the alpha S value is very small, and whatever you take the value the interspace distance, there will be a shadow from this panel on the other series of panels. I mean minimizing the effect of solar panel shading. At least in the middle of the day we have no shading. Okay, there are different ways to calculate the interspace or inter-row spacing. The first is using softwares. Many softwares are available in the market. This is a picture from PV Sol. You can see the link here, which is a photovoltaic design software. In this software, and also in many other softwares, there is an option to calculate the inter-row spacing, and they also enable you to put the panels also in, for example, in a sloped roof or any other case. So the first method is using the commercial softwares for determining the appropriate inter-row spacing. The other is online tools. There are some online tools. This is just one of them. I put here the link. You may enter the values, for example, for the collector angle, the length of solar panel. This is the length of solar panel. If installed in the on the pitched roof, you can enter here the pitched roof degree, roof mount height. This is the roof mount height. You can see here. And then update, you will take here the results. This is also an interesting tool. Or you may calculate it by hand or manual calculation. For manual calculation, here I have shown a picture. You can see that this is there are 3 rows of solar panels, for example, installed here. This is the south direction. This is in Persian, but the meaning is south direction. This is the sun position. Alpha S is sun altitude or sun elevation angle. Beta is the slope of the solar panel installation, as you can see here, and L is the length of panel. In order to minimize the effect of shading on the solar panels, which is installed at the northern side of the southern panel, HC, which is the interspace distance between the solar panel bases, should be larger than L cosine of beta plus this value. So you should calculate the right hand side, and then HC for the installation should be larger than this value. L you may take from the manufacturer data. For example, this is a data sheet from a solar panel manufacturer. In any solar panel catalog you can see the dimensions, then you can take L. Just there are two notes about L. The first is you may check if you want to install the panels in landscape or portrait situation, because if you put them in a landscape situation, then L will be this, and if they are in a portrait situation, then L will be this. You may ask yourself, what's the difference between installing these in a landscape or portrait situation? You may think about this also. We will come back to this when we discuss specifically on shading on solar panels and the effect of bypass diodes. This is a guide just, and you may think about that what is the relation between shading, the type of installation, landscape or portrait, and bypass diode or something like this. We will discuss about that, but for the time being, please keep in mind that for this type of installation, L is the shorter one, and for this type of installation, L is the longest dimension. The other point of importance is that if the panels are installed in this way, for example, in this case, you can see that two panels are installed one above another, then you should take L twice the length of the panel, okay? And apply the same rule here. For example, you may have two landscape type panels installed, then you should take its value. Okay, so L may be calculated as I explained. Beta is known generally when you want to install panels. We discussed about that, I think, last week. And the last thing is alpha S. Alpha S, as you can see here, is the sun elevation angle, but you should take it for the day with the longest shadow length. Why? Because if it works for the day with the longest shadow, then it will also work for other days of the year. Now the question is, what is the longest shadow day of the year? Yes, you are correct. It is 21st or 22nd of December, or in a better way to say, it's the winter solstice, okay? So you should calculate alpha S for the location in question for the winter solstice. Okay, here I draw, for example, the sun path diagram. This is for Baghdad based on the solar time, as you can see here, and I want to show you how to calculate alpha S for the longest day of the year. The other question, okay, we'll come back to this. If you remember, this is the sun path diagram. I think I forgot to say that the horizontal axis for the solar path diagram is the solar azimuth angle. Here is the south direction, which you may take it either as 0 or 180. The case for this graph is 180 for the south, but no problem. You may think of 0 about it. The vertical axis is solar elevation angle or solar altitude angle, or alpha S. So this is the graph of alpha S versus gamma S for this location, which is Baghdad, for example. The blue curves here show the specific days of the year. The top one is for 21st of June, and the lowest one is for December 21st. The red lines here also are the times of the day, for example 6 a.m., 7 a.m. or others. Please note that you can draw this curve by the link which I introduced, either based on solar time or on standard time. This I draw based on solar time because it's more usable for this type of calculation. Okay, so the lowest curve, which is for 21st of December, is for the day with the longest shadow. But the next question is, what time of the day we should take? There are two ways actually. In some cases, they take 12 p.m., 12 or solar noon as the reference. So if you come down here or here, and then take the cross with the 21st of December and then go to the right, you can see that it is 34. What's the meaning? The meaning is that on 31st of December at solar noon in Baghdad, the sun elevation angle is 34, and this is alpha S actually. So alpha S in Baghdad for the winter solstice, which is 21st of December at solar noon, is 34 degrees. So you can take 34 here for the value of alpha S. There is another way actually. Some people use this method and say that this is not a good practice. The better practice may be to have its cross section with 9 a.m. or 3 p.m. solar time. So if you take the cross with the 21st of December, either here at 9 a.m. or 3 p.m. solar time, then the value of alpha S will be 20 or 20 degrees. Then you can take 20 for the value. My idea is that if you have enough time or land for use, then take 9 a.m. or 3 p.m. for determining alpha S. But if your land is limited, then you may take this exercise. You may take 12 or solar noon for determining the alpha S value. Okay, the second type of shading is shading of nearby trees, building, or other abstraction on the solar panel. Suppose that you have a solar panel here, and then at the south direction you have trees or building or some other abstractions. How we can determine the effect of these abstractions on the solar panels? And this is the second type of shading. To calculate the effect of shading, this type of shading, there are some ways again. The first is using the sun path diagram. You may remember that this was the sun path diagram. For example, you may draw the sun path diagram for the location and then put any abstraction on the south direction, for example, a tall building, a small building, a tree, or something like this, for example, here. Then look at the graph. And by looking at the graph, you may conclude some very interesting result. The top curve, as you know, is for the summer solstice, 21st of June. The lowest one, the blue curve, is 21st of December or winter solstice. And the middle one is for the equinoxes, which is 21st of March or 21st of September. And then if you look at the position of the abstractions on this graph, you may see, for example, this building casts a shadow on the collector in the morning in all season, because here is the morning where azimuth angle is negative, and here it is afternoon. And you can see that in the morning in all the seasons, either in December, in March or September, or in, for example, June, and the days in between, in all days from this time where the shading starts up to, for example, this time which the shading will finish, this building casts a shadow on your collector. But this small one, for example, this small building, does not cast shadows on the collector in summer and spring. You can see that it just casts a shadow when the sun rises up to, maybe you should see the timelines. You may remember that there are red curves here which shows the time. I did not draw them because the shape will be very complicated. You may see that, for example, for this building, cast a shadow when the sun starts rising in the winter solstice up to maybe 8 o'clock in the morning or 9 o'clock in the morning. So by the first method is using the sun path diagram. You can do it manually, and use of some tree geometry will suffice to do that. The other way is use softwares to find a shadow effect. For example, this is a screenshot from PVSol software by these softwares and also some other softwares. PVSol has a very interesting shading calculation option. It's really interesting. I did not see similar one in the other softwares. You can draw the system. For example, you may define the tree, for example, its height, its diameter, and many other things, if the leaves will fall in the winter or not. And then, for example, place the solar panel, and you can also animate it during the 365 days of the year to see how it will cast a shadow on the solar panel, and also you can calculate the effect, how much it will decrease the beam radiation on the solar panel. So the next one was the commercial tools, softwares. There are some equipments also which you may use to determine the effect of shading. By the progress of mobile phones and apps and very more sophisticated devices, sorry, some people may not use these equipments, but they are still available, and many people use them. For example, solar site selector, solar pathfinder. You may search in the net by these keywords, and you may find a lot of information and videos about them. There are also some devices which are more new. For example, Solmetric has a device like this one, and some other versions of it, which may be used to calculate the effect of shading by south objects on the solar panel. There are also mobile apps to do that. For example, these are just samples, because I do not recommend either to use or not use them. These are just sample, and you may find a lot more by Googling. This is a mobile app. You should pay for that. For example, you take a picture from the south direction, and it puts the abstraction on the south on the solar path diagram. This is much simpler than drawing this manually. Yes, so this is also a very interesting tool. This is another mobile app for using for determining the effect of shading on the solar panels, and you can see here another one. Okay, this is end of lesson 4. Thank